Alright, so oftentimes when you're dealing in factoring situations, you're facing problems that involve multiple factoring techniques simultaneously, not just one single technique. So as an example of that, why don't we try a problem like this. Let's say we've got 20x to the 8th plus 8x to the 7th minus 45x to the 6th and minus an 18x to the 5th. Now, as it so happens, there's a lot of stuff going on with this particular factorization setup, but regardless of how complicated your factoring problem initially looks, you always want to start with the same initial technique, which is to look at all your terms and see if there's a greatest common factor you can pull out of everything at once. That usually makes your subsequent factoring process a lot easier. So when you look here, you examine all the coefficients and all the variable parts. It looks like the only common thing you've got to everything simultaneously is x to the 5th. So you can pull that out. That leaves behind then a 20x to the 3rd plus an 8x squared minus a 45x and minus an 18. Now, at this point, a lot of people stop and say, I'm done. I did factoring. That's all there is to it. There's nothing left. But in fact, that's not the case. Every time you finish a step in a factorization procedure, you want to look at the stuff you've generated and see if the leftover factors match any techniques that you still have and haven't used yet. So for example, here, that x to the 5th is a monomial. You can't factor that any further. But now, this thing that's left over here, this 20x cubed and so on, it's a polynomial with an even number of terms, 4 or more, so it's possible that you might be able to attack this by grouping. So try grouping up the first half of the terms separately from the last half and see if you can perform little greatest common factorizations on each group. So here, when you look at just the first little group on its own, you can get a 4x squared out of that, and that leaves behind in that first little group a 5x plus a 2. And then in the second little group, well, you can take the leading negative out of that second little group, and in addition to that, it looks like you can get out a greatest common factor of 9. So that leaves behind then, again, 5x plus 2. And that's the key signal for a successful grouping. Now we've got exactly the same leftover polynomial piece in each of those two overall terms, so you can factor out now that 5x plus 2 is common. So there's the x to the 5th we pulled out at the beginning. Here's the 5x plus 2 that comes out as common. And that leaves behind then as leftovers 4x squared from the first term and minus 9 from the second one. So there's the grouping stage now with this problem is complete, but that doesn't necessarily mean you're finished yet, because when you look at what you've generated now, again, the x to the 5th is just a monomial. Nothing else is going to happen with that. 5x plus 2 is just a linear factor. It has no greatest common factors, no grouping potential. It's certainly not a trinomial, no squares or cubes, so there's nothing you can do with that. But now when you look at this thing here, 4x squared minus 9 is the format that we have a technique for, because that's a difference of squares. So that admits one more factorization. So all the complete stuff carries down from before, the x to the 5th, the unfactorable 5x plus 2. But now finally this 4x squared minus 9 is a difference of squares, where the things being perfectly squared are 2x and 3. So that factors down 2x plus 3 times 2x minus 3. So now there's another stage in your factorizations complete, and when you look at this now, scan all your results, especially these new two you just generated here with the 2x plus 3 and 2x minus 3, and you can see they're both linear factors. Linear factors don't factor down any further, so there you are. X to the 5th times 5x plus 2 times 2x plus 3 times 2x minus 3 is your fully factored final result.